Alright, welcome to Unit 7, Torque and Rotational Motion. This is the second video. This one will be specifically on torque and rotational inertia. So let's get into it. First, what is torque? So torque is a measure of how effectively a force can cause an object to rotate. Note that it is a measure of how effectively a force can do that. It is not a force. Torque is not the same as force because its units are Newton meters. And this is the formula Rf sine theta, or R perpendicular to F, or R cross F. All of these basically mean the same thing. What they mean is that when you multiply a radius by a force, you're only looking for the perpendicular component. So both radius and force need to be perpendicular to each other for you to just multiply them. So for example, in this, since both are at a right angle, we can say torque equals Rf. But if we have a more complex example, like if we have a circle here, and this is the radius, and the force is applied like this, we can't just say torque equals Rf, because there's an angle, this angle right here, theta, that needs to be accounted for, and in order to get the horizontal direction, as you can see, opposite over hypotenuse, that's sine, to get the perpendicular, so we would do sine theta, which is how we get that formula, which is why it's also expressed as perpendicular or a cross product. Alright, so here's some more about torque. So as I touched on the last slide, torque is not equal to force because they have different units, newtons versus Newton meters, and they function differently. However, we can say that it is the rotational equivalent to force in the case of many formulas when you're drawing parallels between like linear dynamics and rotational dynamics. And torque is a vector, so it has magnitude and direction. And if net torque on an object is 0, we call that rotational equilibrium. Remember that if net force is 0, we call that translational equilibrium, and if both are at 0, we can call that static equilibrium, which will be useful in later problems. So our first example, we have a captain of a ship turning a steering wheel by applying a 20 Newton force at a radius of 0.2 meters at an angle of 80 degrees. So if we write out our torque equation, we have R cross F, or Rf sine theta. If we draw it on our steering wheel over here, we can draw the parallel line to the radius, our force, at 80 degrees, and 20 newtons, with this being 0.2 meters. We want the perpendicular component only, so we would do 0.2 times 20 times sine of 80, which is equal to around 3.94 newtons. So that example was pretty simple. Let's move on to a slightly more challenging one. So in this example, we have a 15 kilogram box sitting on a lever arm a distance of 5 meters from the axis of rotation. The question is asking what distance another 10 kilogram box has to sit to create a clockwise moment that will result in a net torque of 0. So in simpler terms, it's asking where the box should be placed for it to balance. So if you look at here, it's given to us that this distance from the pivot point is 5 meters, and we want to have another 10 kilogram box at a distance, let's call it R, so that the net torque is 0. So if we want to write this out, we can say torque clockwise is equal to torque counterclockwise. So on the counterclockwise side, we would have the 15 kilogram mass, and on the clockwise side, the 10 kilogram mass. So if we're doing force, so we do force gravity times R is equal to force gravity of the other box times 5. So that means this would equal, let's say 100 if we're estimating G to be 10, times R is equal to 150 times 5. And then by simple math we have that R equals 7.5 meters. So this box would have to be placed 7.5 meters from the pivot point for the seesaw to balance. And if we do that in our head, it makes sense because we know that torque equals radius times force. So if the box has a lesser gravitational force because it has a lesser mass, then it would have to be placed further to have the same torque effect as the more massive box. Okay, so now let's move on to another example. Example 3. So we have a uniform wooden block with mass m, and on top of it is half of this block and put on the left side. So there's also two legs supporting the both boxes. So the first one, which table leg should provide a larger force. So let's go to our diagram. Let's set up the axis of rotation right in the middle. So first of all, the mass and force that the bottom block applies no longer matters to us in torque calculations because its center of mass is right in the middle because we know it's uniform. And that means that the force of gravity is coming right from the middle for this bottom box, which means that we can ignore it because it's at a radius of 0 from the axis of rotation, and torque equals force times radius. So then, let's look at other torques. Let's look at the smaller box, for example. Since we know it's exactly half of the bottom box, it has mass m/2. And we know that this length is L/2, which means that the center of the smaller box would be at L/4. From the center of the big box, which means that the torque in total would be the force of gravity coming from the smaller box times the radius from the center, which would equal m/2g times L/4. And this force would be going in the counterclockwise direction. So if we do torque clockwise equals torque counterclockwise, that would be on this side. And what else would be going counterclockwise? Well, the force from the right leg of the table and the torque coming from that. So we draw an arrow up because the right one will push up on the table like this at a distance of L/2 because it's on the far end of the center, which is L/2. Both L/2's add up to make one L. So let's call this upward force Fr. So we add that to the counterclockwise side plus L/2 Fr. And then on the clockwise side we only have one force, that being the left leg of the table, which also goes up. Let's call that Fl, and that is also at a distance of L/2. So we do L/2 times Fl. So right off the bat, without solving for anything like Fl or Fr, we can see that Fr has to be added with another torque to produce the same torque that Fl does, which means that Fl has to have a stronger force than Fr because it's doing more work. It's supporting both this counterclockwise torque of the smaller box added to the counterclockwise torque of the right leg, which means that for this one, the table leg is left. And then for the force of the right hand table leg on the bottom mass, we just use the equation we got in A. And what we would get is Fr equals Fl times L/2 minus mgl/8. All of that times 2/L, which means L's would cancel, and so would 2's make this a 4. So Fr would equal Fl minus mg/4. Alright, so that was example 3. Let's move on to another concept, rotational inertia. So in rotational dynamics, instead of mass, we would use rotational inertia. So for our dynamics, like normal dynamics equivalent in rotational dynamics, we have rotational inertia instead of mass. So for example, our formula F equals ma, which I will write up here. We had F equals ma, so the equivalent of force would be like torque, A would be like angular acceleration, which we talked about in the last video, and m would be like I. So what is I exactly? It is an object's ability to reduce changes in its rotational motion. So it's really similar to regular inertia, especially the definition, except it's just for rotation because we're talking about rotational dynamics right now. So the formula is I equals epsilon mr squared. Epsilon is just a constant that changes depending on what object we're talking about. So for example, you have a hoop and its axis of rotation is through the middle, and this is the hoop and the mass is shaded. This hoop has higher epsilon value and higher rotational inertia because more of its mass is concentrated further from the axis of rotation, which goes through the middle, and the mass is all on the outside because it's a hoop, and because of this the epsilon would be higher compared to, for example, a sphere. A sphere is shaded in completely. Let's say it's a solid sphere. Therefore, it would have a lower epsilon value regardless of the axis because more of the mass is concentrated near the axis of rotation. And that's how it varies from object to object. We'll get into more examples on the next slide. Alright, so these are the examples. Let's go over them. So first we have a solid cylinder or a disk with a symmetry axis going through the middle as shown. So what this is akin to is a pulley. So whenever we see pulleys going forward, their rotational inertia will be 1/2 mr squared because they are just cylinders with very short heights, but they are still cylinders, solid cylinders with the axis going like this. That's how they rotate. If you had two ropes going on both sides, it would look like this, for example. And yeah. Then we have the hoop, which I talked about on the last slide, equals mr squared. However, it's not just a hoop that has mr squared, or point mass. So any point mass would also have a rotational inertia of mr squared. And then sphere, we talked about having lower epsilon value than a hoop. It's 2/5. Rod about center, 1/2. Rod about end, 1/3. Even though both are rods, because the axis changed, the rotational inertia also changed, which is important to know. This is a spherical shell. Since shells have more mass on the outside, its epsilon value went up compared to the solid sphere. And with a hoop about the diameter, it's 1/2 compared to a hoop about its symmetry axis, which would be like it's spinning. So that's another difference. And a solid cylinder on the central diameter is a more complicated formula that uses both the radius and length because of how it's spinning. But you most likely won't need this one anyways. So you don't need to know any of these usually. Most of the time it will be given to you. However, two that you should know is that for point mass / hoop, epsilon is 1. So this, and cylinder, which is this one, pulleys, 1/2. So 1 for point mass and hoop, and 1/2 for cylinders. And if you have a system of multiple objects, you can add the rotational inertias together. Alright, so next part. Rotational inertia and torque. So rotational inertia is tied to torque by a similar formula for Newton's second law in linear dynamics. So F equals ma changes to net torque equals I times A, which we talked about a couple of slides ago. But here it is written out explicitly. So net force, net torque, linear acceleration, angular acceleration, mass, rotational inertia. So yeah, pretty simple and straightforward transition between normal dynamics and rotational dynamics. And remember that the torque is net, and in order to calculate angular acceleration, we can use change in angular velocity, position, time, basically all of your kinematics equations that we talked about before. And we can also use graphs if they're given. Okay, so let's move on to a simple example. We have a disk with a mass of 2 kilograms, radius 0.1 meters with a net torque 10 Newton meters. It's asking for the angular acceleration. So since no angle is specified, we can assume that this is applied perfectly perpendicularly, so no angle needed. We'd say torque equals rotational inertia times angular acceleration. And angular acceleration is what we're solving for. And rotational inertia, remember, this is a disk, which is the same as a pulley or cylinder, so its rotational inertia will be 1/2 mr squared. For torque it's given, so 10 equals, for rotational inertia we do 1/2 times 2 times 0.1 squared, and then that would be multiplied by the angular acceleration. So when we solve for that, we would get 10 over 0.01, which equals 1,000. So 1,000 with units of, since this is angular acceleration, radians per second squared, which got cut off a bit, so I'll write it down here, radians per second squared. Okay, so that is rotational inertia. Let's move on to a complex example that combines everything we've learned so far. A sphere with mass m and radius r rolls down a ramp that makes an angle theta with the horizontal. The moment of inertia is the sphere is given as 2/5 mr squared. And the sphere rolls without slipping, which is very important, which means that we can work with torque freely without worrying about any frictional force that's impeding or causing any other change in the system. So let's move on to part A. We're given a diagram, draw and label all the forces acting on the wheel as it rolls. Clearly indicate which point on the sphere the force is acting. So first, let's consider the middle of the sphere. We already know what acts from there. We have first the force of gravity, as well as the normal force, which would point this way because it's on an inclined plane. And then from the bottom of the sphere, we also have a force of static friction. So even though it said rolls without slipping, this force of static friction still exists because it's what grips the sphere to the ground as it rolls. It's similar to how in cars, the tires spin the reverse way in order to make it so that the grip of the tires sticks to the floor, so that the static friction propels the car forward using torque, which is important. So then it asks, as the sphere rolls down the ramp, which force causes a change in angular velocity with respect to its center of mass? So all this is asking is what is causing the net torque. And it's obviously going to be friction, because both of these act from the center, and as we know, if you act from the center of the the axis of rotation, you can't apply a net torque, so it's just friction for the reasons that we just talked about. Then let's go to part B. What I meant to say is let's go to part C. So part C. In terms of mr theta and other constants, what is the minimum force of friction necessary to keep the sphere rolling without slipping? So the sphere, the static friction pointing this way, what is the minimum value so that it still has enough grip to keep the sphere rolling without slipping? So in order for that to have enough grip, the angular acceleration has to be held intact, so we'll use net torque. So torque net equals IA, and as we remember from the previous slide, the only torque on the ball is static friction, because it's the only one that acts from a radius. All the other forces act from the center, so they can't have torque. So we'll write Fs for static friction times r, which is the distance that the force is applied from, and it is perpendicular. If you can see the diagram, you see that's parallel to the ramp, and then the force will be parallel to the ramp, and the ramp is perpendicular to the radius, which creates a right angle, which means that we can just do Fs times r equals I, which is 2/5 mr squared, and angular times angular acceleration. However, if you remember from the previous video, angular acceleration is nothing but linear acceleration a over r radius. So if we plug that in, we get Fs r equals 2/5 mr squared, all of that times a over r. So what would happen here? This r cancels with that r, and then this r would again cancel with this r. So all we're left with is that Fs equals 2/5 ma. However, we're not done yet, because we need the answer in mr theta and other constants, and a is not a constant. So now we move on to our other equation that we're going to need to use. So let's get rid of some of this first. In this case, in a few moments, we'll be using the net force equation, because that is something we'll need to get rid of the a and substitute it with another value that is more appropriate for what we need the equation to be in terms of. So let's look at that. Net force equals ma, as we know too well. So net force, what is the net force? So we have one force on the ball, if you look up here, acting down this way. That is the horizontal component of gravity acting from the center, but I'll just draw it there. That will equal mg sine theta. And then we have a force acting the other way, force of static friction, Fs. So this means that this is equal to mg sine theta minus Fs equals ma. And what do we know Fs is? 2/5 ma. So let's plug that in. Mg sine theta minus 2/5 ma equals ma. So first of all, m's cancel, and we get 7/5 a right up here. 7/5 a equals g sine theta. This means that a equals, almost right up here, a equals 5/7 g sine theta. We can plug that in down here to get Fs equals 2/7 mg sine theta, and that is our final answer for C. Alright, so part D asks to solve for the acceleration of the sphere. But we already did this to solve for friction in terms of the given constants, so I'll just write out acceleration again. We got 5/7 g sine theta. Remember, we got that by combining the net torque and net force equations and using the commonality of static friction between both of them. So with that, let's go to part E. The sphere is replaced with a cylinder, same mass and radius. Will the cylinder have greater, less than, or equal to acceleration? So I'll give you a couple of seconds to think about this. Okay, so the answer is less than. Why? It has to do with rotational inertia. Cylinder is 1/2 mr squared. Our current one, the sphere, is 2/5 mr squared. Remember that net torque equals IA, and torque in this case won't change because that equals force of friction times radius. It gives us that the radius is the same. Force of friction won't change because mass is the same, which means that torque stays the same. Inertia will go up for the cylinder, right? Which means that rotational acceleration will have to go down because it's inversely proportional to inertia if the torque stays the same, which it does in this case. So I'll make some space. We can write that like this. I'll just put a check here again. Since cylinders have higher rotational inertia than spheres, and because torque stays constant, angular acceleration will decrease per t equals IA. When angular acceleration decreases, and we know the formula, A equals angular acceleration over r. Remember, r is also constant, so if A goes down, r stays the same, then this big A will also go. This other A, English A, for linear acceleration will also go down because it is directly proportional to angular acceleration. When A decreases, so will linear acceleration, which is normal A, because, and then we can write the equation, which I don't have space to do, but you get the idea. And that is our reasoning. Okay, now for the last example, probably the trickiest one for people at least, static equilibrium. So a 50 kilogram box is hung from a 5 meter long, 200 kilogram horizontal pole as shown above. A wire is attached to prevent the sign from rotating, and the box and wire attach at the right end of the pole as shown below. Find the tension in the wire. So first, we want to choose a spot for our pivot point. The best spot would probably be right where the pole hits the wall. Why? Because we don't have to worry about what the forces of the wall is exerting up and towards the right. We can just ignore all of that. Now let's deal with the problem. So because the system is not moving at all, we have two things. Net torque equals 0 and net force equals 0. For this one, let's focus on torque. So first of all, we have many torques going on, but we're going to have to break the tension force into components to see some of them. For example, the tension force goes like this, but tension Y will go like this, and tension towards X will go that way, Fx. So I'll just erase the total component to make room for the horizontal and vertical one. So it's like this. And as you can see, the horizontal tension force won't apply a torque because it's going in the same direction as the axis of rotation. It's not perpendicular to the radius, so we can get rid of that too. So only the vertical component of the tension will do anything. So if we write torque of tension Y is equal to Fty times the distance from our pivot point, which would equal 5, which is given, so 5. But then what other torques are there on the system? First of all, the pole has a mass, and if the pole is uniform, which we can assume, then its center of mass will be right in the middle, which is 2.5 meters from right here, and that would be Fg of the pole. And that would of course just be 2,000 newtons because 200 times 10. So if you write T pole, that equals 2000 times, and then 2.5 for distance from pivot. And there's one more torque, the box T box. Of course it points straight down. Actually, let's label these. So this one pulls up like this, so that's counterclockwise. This one pushes down, so that's clockwise, and this one also pushes down, so clockwise. And then this one, what would we saying it's equal to? Just the gravitational force of the box, so that's 550 times 10, 500, times distance from pivot point, that's 5. So if we set up our equation, torque, because net torque is equal to 0, we know that torque CCL has to equal torque CL, so that's box plus pull equals tension Y, which will be FTY times 5 is equal to 2000 times 2.5, that's 5000 plus 2500, so that would be 7500, so FTY we can say would equal 1500. So let me just clear space and write FTY again. If FTY is 1500 newtons, and we know that FTY is equal to FT sine theta, which is given as 30, so let's just replace that with 30. And then that is also equal to 1/2, so FTY is equal to FT over 2, which means FT is equal to 3000 newtons, and we're done. So that was our last example, static equilibrium. So yeah. Thanks for watching. Remember to like and subscribe. Next video will be 7.3 rotational kinetic energy / angular momentum, and that is it. Thank you. Bye.